Welcome back to the workshop for one last example on power series representations of functions. I'm really excited about this example because there's a few different aspects that we need to be thinking about from our knowledge on power series that we've already considered, not just our ability to represent functions using the geometric series. Of course, we'll use that here as well. What we actually want to use first, before we can apply the geometric series, right? I can't write that as a geometric series as it is. But what I want to do is I want to recognize that this is the integral. Now, maybe we would have to use a definite integral here. So there's going to be a c value here because we have an integral that constant of integration that we'll have to deal with. But otherwise, this is the integral of 1 plus x squared dx. And that's fantastic because 1 plus x squared, that looks very similar to the sum of a geometric series. And this allows us to say that if I were to take the derivative of both of these things, then g prime of x is equal to 1 over 1 plus x squared. So I can find a geometric series representation for g prime of x, and then I can take the integral of that power series to get the power series representation for g of x. Again, I'll get a constant of integration there that I need to find a value for, but other than that, pretty straightforward. All right, so g prime of x is this. But this is equal to 1 over 1 minus negative x squared. Okay, so it's the negative of x squared. That's going to be our value for the geometric series. So this is the sum from n equals 0 to infinity of, let's see here, n equals 0 to infinity of, the a value is 1, the r value is negative x squared, raise that to the nth power. So this gives us a power series representation, and this for our g prime of x, and I can write this as the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n. Excellent. That's not so bad. Not so bad at all. All right. Maybe leave a little bit of room right here or here, as I have, for an additional comment that we'll return back to. Okay. Then g of x is equal to the integral of g prime of x dx, which we can use the power series representation for. So this is the sum from n equals 0 to infinity of constant multiple just gets carried along, so negative 1 to the n, raise the power by 1, x to the 2n plus 1, and then divide by the new exponent, 2n plus 1. Here it's important to remember that n, for each term in the series, n is just a constant. So it's not a variable here, it's an index. And at each term, we're looking at a fixed value of n. So the only variable is x, everything else is a constant. Of course, we need a plus c. And let's see, what we want to think about values of the arctangent that we know. And the arctangent, right, tangent is sine over cosine. So the arctangent of 0 is when tangent is equal to 0, and that would be when sine is equal to 0. So again, our angle there would be 0. So we get this g of 0 should be 0. G of 0 should be 0. But if we were to plug 0 in right here, right, that makes every single term 0, leaving us with just C. So g of x is equal to the sum from n equals 0 to infinity of -1 times x to the 2n plus 1 divided by 2 times n plus 1. All right. From here, we just want to determine the interval of convergence. And if we were to consider this representation right here, we would recognize that we no longer have a geometric series, so we can't simply say R is this, and we need to, well, I suppose we probably could represent it as a geometric series still. Oh, I'm missing an N here. Sorry about that. So I could, let's see here. Well, I could represent this as a geometric series, it appears, but I could also have started over here, which would have been a little bit easier. This is a geometric series, we know that, and this would give us an interval of convergence from -1 to 1, which may not be immediately obvious, but I trust you to determine that on your own. And then when we look at the integral or derivative of a power series, the interval of convergence is the same with the exception of endpoints. We may or may not include endpoints. So you'll find that the interval of convergence here, so this is with interval of convergence, again, the interval is the same with the possible exception of endpoints. So it's going to be from -1 to 1, and you should test the endpoints. In this case, if you use -1, you would find that this is, let's see, that's always odd. So we should actually find, in this case, unless I'm going a little crazy, which happens, let's see here, if I plug in -1, 2n plus 1 is always odd, so that's always just a -1. So we have some sort of a version of the alternating harmonic series. So it appears that that should actually converge. And the same is true at 1. So it looks like we're actually going to get convergence at -1 and 1 here. So I'm going to... Oh, yes, of course, we could not write this as a geometric series because our A value would have an N in it, and that doesn't quite work, or at least that's what I was imagining in my brain. So, not a geometric series. We test the endpoints. We find that the interval of convergence is from -1 to 1, including the endpoints. All right, excellent. Thank you for your attention. I'll see you guys again soon, back here in the workshop.